Assalamu alaikum. My name is Rubaya Sharmi. In our research, we are four members: Hamid, Samantha, and Mohaiminul. In our research, we are going to discuss about neuromorphic computing system, device level, the future of neuromorphic computing, challenge of neuromorphic computing system, with introduction. Introduction. Neuromorphic computing is known as a neuromorphic engineering, being the huge redesign from man-made conclusion in the future is going. Neuromorphic figure depends on the human organic mind. In our organic mind, there are billions of neurons. Those neurons will work till our dismiss. Those join through our neurotransmitter. Neurotransmitter is an intersection of changing neurons and their connection to another. A key aspect of neuromorphic engineering is understanding how the morphology of individual neuron circuit application and overall architectures architecture creates the disable competition and expect how information is represented in influence to damage and incorporate learning and development, adapt to local change and facilities evolutionary change. A key feature of biological brain is that all of the processing in neurons use analog chemical signal. This make it hard to replicate brains in computer because the current generation of computer is completely digital. However, the characteristics of these parts can be abstracted into mathematically function that closely capture the inside of neuron operations. My next part is going to be present by Muhaiminul.
So I am Mohaminul Islam and my presentation topic is neuromorphic computing system level and device level. So in system level, traditional computational architectures and their parallel derivatives are based on a core concept known as the von Neumann architecture. We can see this in figure 1. The system is divided into several major physically separated rigid functional units such as memory, unit, control, processing, CPU, arithmetic and logical unit, and data paths. This separation produces a temporal and energetic bottleneck because information has to be shuttled repeatedly between the different parts of the system. This von Neumann bottleneck limits the future development of revolutionary computational systems. Traditional parallel computers introduce thousands or millions of conventional processors each connected to others. Aggregate computing performance is increased, but the basic computing element is fundamentally the same as that in a serial computer and is similarly limited by this bottleneck. In contrast, the brain is a working system that has major advantages in these aspects. The energy efficiency is markedly many orders of magnitude superior. In addition, the memory and processors in the brain are collocated because the constituents can have different roles depending on a learning process. Moreover, the brain is a flexible system able to adapt to complex environments, self-programming, and capable of complex processing. While the design, development, and implementation of a computational system similar to the brain is beyond the scope of today's science and engineering, some important steps in this direction can be taken by imitating nature. Clearly, a new disruptive technology is indeed which must be based on revolutionary scientific developments. In this neuromorphic architecture, we can see this in figure 1. The various computational elements are mixed together and the system is dynamic based on a learning process by which the various elements of the system change and readjust depending on the type of stimuli that they receive. And in figure 1, the comparison of high-level conventional and neuromorphic computer architectures, the so-called von Neumann bottleneck is the data path between the CPU and the memory unit. In contrast, a neural network-based architecture combines synapses and neurons into a fine grain distributed structure that scales both memory and compute elements as the systems increase in scale and capability, thus avoiding the bottleneck between computing and memory. And in the next slide, device level, A major difference is also present at the device level. We can see this in figure 2. Classical von Neumann computing is based on transistors, resistors, capacitors, inductors, and communication connections as the basic devices. While these conventional devices have some unique characteristics such as speed, size, operation range, they are limited in other crucial aspects such as energy consumption and rigid design and functionality, inability to tolerate faults, and limited connectivity. In contrast, the brain is based on large collections of neurons, each of which has a body, synapse, axon, and dendrites that are adaptable and fault tolerant. Also, the connectivity between the various elements in the brain is much more complex than in a conventional computational circuit, which we can see in figure 2. So in figure 2, interconnect, we can see this interconnectivity in picture A and picture B neuronal circuits. So that's it. My next slide is going to be presented by Samantha.
Assalamu alaikum. My name is Samantha. My topic is Neuromorphic Computing Challenge. Neuromorphic computing is an emergent field of technology that is mostly still being researched. Only recently have there been any attempts at the practical use of neuromorphic computer architectures. The most recent developments in neuromorphic hardware have the potential to improve the efficiency of current neural networks, which currently run on somewhat inefficient graphic processing units (GPU). However, a functional human brain chip is still a long way off. One main challenge facing the field of neurocomputers put forth by expert Katie Suman in an interview with online magazine Ubiquity is that it is dominated by hardware developers, neuroscientists, and machine learning researchers. It is lacking in software developers and engineers. In order to bring neuromorphic system into production, a change in thinking is required. Developers, researchers, and engineers need to be willing to move beyond the current mood of thinking about computer architecture and begin thinking outside of the traditional von Neumann framework. Eventually, in order to popularize neuromorphic computing, software developers will need to create a set of APIs, programming model, and languages to make neuromorphic computers accessible to non-experts. Researchers will need to develop new ways to measure and access the performance of this new architecture so they can be improved upon. They will also need to merge research with other emergent fields such as probabilistic computing with aims to help AI manage uncertainty and noise. Despite these challenges, there is significant investment in the field. Although there are skeptics, many experts believe neuromorphic computing has the potential to revolutionize revolutionize the algorithmic power, efficiency, and overall capabilities of AI, as well as reveal new insights into the cognition. My, my next part will be presented by Hamid.
Assalamu alaikum. I am Hamid Ajad, and now I am going to tell about future of neuromorphic computing. The advantage of neuromorphic computing comes from the previously mentioned strong points of the technology. All processing can be done locally inside the brain of the neuromorphic chip. This will reduce latency, reduce energy cost, and increase the neuromorphic chip's autonomy, while also improving a sensitive part of the neuromorphic chips as most data is processed locally, like cybersecurity. It will also open many new capabilities for another growing industry, that of the Internet of Things. These devices are known to be very sensitive when it comes to energy consumption, as they have limited supplies of battery life. Small and very efficient neuromorphic chips about be used to give more utility to each device at low costs. Now, in the conclusion, we can say that the deep learning industry needs a new type of hardware, numeric hardware, to be truly efficient. Neuromorphic chips show great promise to be the best fit for it, and some companies are working towards developing this technology and the future of hardware artificial intelligence. Hopefully, the industrial research in this area will increase and we will soon have hardware dedicated for neural networks. In short, neuromorphic computing has the potential to help to design better, faster algorithms with the additional benefit of helping us better understand the brains. That's the end of our topic. Assalamu alaikum.